couple things to talk about before we finish. Boundaries. And this will sound totally unprofessional, but maybe you shouldn't trust everything I say here. It's mostly true. Sort of. I haven't really worked out all the details for everything yet, so I'm just saying. I could tell you I'm right. Don't challenge me, but I'm just going to tell you. Boundary conditions, I have it sort of mostly figured out on the D of N, but I haven't worked with DNF to really nail it down. Exactly. Okay. I actually might be right. Are you guys confident yet in this class? Like I said, this is bad form usually, but I'm just going to go out there and say it. I'm going to put it myself. I might be right today. I know I'm right up to there, but right here, this is where it gets a little sketchy. So we want to think about, when we work with this right now, no boundary condition are imposed at all, right? But part of what we want to do is start thinking about, well, how do we impose boundary conditions? We have a derivative matrix, but ultimately, if we're going to solve something, we're going to impose boundary conditions on our PDE of some sort. How do we impose those? Okay? All right. So that's what we have to ask. A couple comments. Well, we didn't really work out an FFT. No. FFT didn't work at it because FFT just imposed periodicity for you, period. It just said, I'm working with it. If you remember, in the ABC matrices, we did work pretty hard at figuring out what to do at the edges. I mean, right? And even in homework 1, right? Or homework, was it 2, right? Where we were trying to figure out how do I impose this going to 0 stuff. You had to come back in and change the matrix. Same thing has to happen here. We have to change that matrix D of N. Okay, so let's talk about first one boundary to impose. Pinned. This is a very simple boundary. Generically, what this wants to do, if you're going to connect it to Cheb, is it's going to want to impose no flux. Okay? How do I change the boundaries to say, well, I actually want pinned? In fact, generically, you might even think about, well, actually, maybe I even want, like, this is some alpha, and this is some beta. So in some sense, you already know what the boundaries are, right? So when you start thinking about what this matrix does, you start thinking about, well, I have this matrix multiply that's going to happen for my points. And you look at it and go, wait a minute, but V0 and Vn are 0 already. What did we do in homework 2 with those? We kind of took them out of the problem, didn't we? Remember, we chopped them n plus 1 points, but when we solved that eigenvalue problem, didn't we solve it on a n minus 1? Right? So you had these 2 extra points, you threw them away. You glued them back on later. We got glue. We can put it back on. But in the meantime, it's like, I already know the boundaries. I don't need to solve for them. So really, when I think about doing this, really it's this V1 through V of n minus 1 that matter. So I get this differentiation matrix, and really it's this inner square that really ultimately counts for everything. So what I really want to do then is start working with, to impose 0, I just say these are 0 at the edges. And really what I want to do is now start thinking about when I take derivatives, I'm not working with this whole thing. I'm working just with the subset of the whole thing. And so you might say, well, I pulled out, so for instance, yeah.
V1 equals 0, so you're saying that the function is 0 at the boundaries, but then you're also saying V minus 1 equals out.
Oh, that's enough. You could do something more arbitrary. Sorry. So let's for this. But the point is, even if I did this, the point is, they're solved for. You shouldn't be solving for them in your problem. What you should be solving for now is all the interior points. Okay.
Flux. Like
So this
is V prime.
No. So this is not no flux. What if you connect this to Cheb, it will want to be no flux, and we want to actually overwrite that and say no, it's not no flux. I want to impose this. if I impose that, these are already determined versus what Cheb would normally want to do, which is impose no flux by using the Cheb polynomials.
So if you put that condition directly into Chebychev polynomial form, you would get a no flux. You would add an extra boundary condition or something. Change it.
I'm not sure if I understand the question.
Is no flux the V prime zero?
Yeah, right. No
You're
flux.
saying that that condition there, if you just, you're saying that would lead to a no flux, that V prime is zero with boundaries?
If I didn't do anything with the boundaries. So if I didn't work with a smaller subset. So what we're going to do is say here's the D of n, but really what I want to do is not work with the V of n. I want to call this Cheb, right? I get these things out. And if I put an n, this is an n plus 1 by n plus 1. So it gives me this big matrix. But really, I already know the boundaries. So all I want to work with is the middle of this thing, because I want to overwrite what the boundary conditions Cheb will do to my thing. And so what I want to do is basically impose that. And so to do this, what I would do is take out, let's say, let's call it tilde d, which will be d 2, n 2, n. What does this do? It goes to the second row. This is n plus 1. So it pulls out everything but peels off first and last row, first and last column. Now I'm working on a subset that is only going to work with the middle points. Yeah?
So does tilde d then have no flux boundary conditions too, or does it have no boundary conditions?
No. So it has no boundary conditions on it associated
How
with
can
it.
you do that? How can
Because
you
now you're
solve-
imposing these guys.
But you're not. You've taken them out of the problem.
It always comes back in, remember? Remember when we did the discretization? It's going to come back into your original problem. Right, so this is just the derivative portion.
Sure,
That you're
but
gonna
without
use.
the derivative, I mean, you have the derivative, so you know how it's going to behave, but without, like, something on either, I mean, I don't know, you're solving a second order differential equation with no boundary conditions. It's
So
too
remember when
many
you did the discretization of the full problem, if you remember homework 2, the boundary conditions actually came back in. Not through the derivative function itself, it came in on the right-hand side, did it not? If you remember, we had those boundary conditions when we were discretizing over here. You had the derivative matrix, which still looked exactly the same, but this neighbor here wanted these 2 points. There's no point over here. We knew what the boundary point already was, and that came actually to be on the right-hand side of the equations of the OD45, or sorry, of the solver, right? So when we did that, that came back into the equation. Actually, in that case, because of the way we imposed it, it came back in to enforced information here, because we knew what it was. And so this is just the differentiation matrix that we had originally built. This is not solving the PDE. Let's not get those two mixed up, right? I still have to impose these back on the PDE. I haven't done that. I'm just saying that for right now, this is my equivalent of my differentiation matrix that we had in class previously. I take away the edges. I still have to enforce these back in the full PDE. I haven't written a PDE down yet, right? So until I write down a PDE, you actually don't have enough information to go back and enforce anything, right? But the point here is just simply that you don't take a differentiation matrix of the whole thing now, because these are known. And you ask how these come back into the original problem. Well, you have to see it comes back in a very specific way, depending upon what your PDE actually is, or your differential equation.
So you ignore the boundary because B0 and Bn are zeros. What if they're alpha and beta? Then
They're also come back right back in. It's just alpha and
wouldn't they
beta.
have an impact on W? We should say W0 is always going to be alpha or beta alpha as well. So because alpha times that top
Right. So
row is always
all this is saying is the only active points you're going to actually evolve in time are the middle points. Let's say if you're going to solve a PDE, the edges are fixed, right? And then imposing boundary conditions is a little trickier. This is why it becomes kind of weird with this, because now you still, just like in homework 2, you have to figure out how do I impose boundary conditions back into my dynamics. I haven't talked about that. All I know is that when you work with this, these are known. You're working with you're working in the middle of your domain. The edges are fixed. Now you're solving the dynamics in the middle. You still have to connect. In other words, these now become forcing terms into the middle. They're known. And that's how you do the connection. Yeah?
This two vectors has actually n elements or n plus 1?
This is n plus 1 elements. And so now you end up with an n minus 1 minus n minus 1. Okay?